Look at this tiny, almost cute little pellet. Something this small can carry a terrifying amount of power, and it comes from a material now sitting at the center of a global crisis: uranium. This single uranium fuel pellet is often compared to about 1 ton of coal. Hard to believe, right? That sounds almost impossible. How can something smaller than a jelly bean hold that much energy? Where does that power actually come from? And more importantly, how do we even turn a dusty old rock into this high-octane fuel? Today, we're tracing uranium from the mine all the way to the reactor. Stick around, because by the end, this tiny pellet will lead us to a question that still divides scientists, governments, and ordinary people. To understand why uranium matters so much, you have to look at it like a long-running mystery. For a long time, uranium held enormous potential, but humanity simply didn't have the key to unlock it. It all started back in 1789 when a German chemist named Martin Klaproth first identified it. Back then, it wasn't special. It was just another element on the periodic table, essentially a fancy rock. It sat on the shelf for over 100 years until 1896, when Henri Becquerel realized uranium was giving off its own invisible energy. Imagine picking up a stone and realizing it's vibrating with its own internal heat. That was his aha moment. This discovery was what inspired Marie and Pierre Curie to dedicate their lives to uncovering even more radioactive secrets. But even then, nobody knew how to actually use that energy. That changed in 1932 when James Chadwick discovered the neutron. Think of the neutron as the silver bullet, a tiny particle that could finally penetrate the heart of an atom. The grand finale happened in 1938. Two scientists, Otto Hahn and Fritz Strassmann, decided to play target practice. They fired those neutrons at a rare version of uranium called U-235. The result? The atom didn't just absorb the hit, it literally split in half, releasing a massive, staggering burst of energy. That was the moment people realized just how much energy was hiding inside the atom. If the key to unlocking nuclear power has already been found, why can't someone just grab a handful of uranium from the ground and toss it into a reactor? Well, as it turns out, nature doesn't make it that easy. Natural uranium is mostly uranium-238. Only a tiny fraction, about 0.7%, is uranium-235, the isotope that can sustain the chain reaction needed in most reactors. To run a power plant, a much higher concentration of uranium-235 is needed. The process of sorting them out is what's known as enrichment. During World War II, the US government assembled brilliant minds like Robert Oppenheimer and Enrico Fermi for a top-secret mission called the Manhattan Project. Their goal was to figure out how to separate atoms that are almost identical in weight. They eventually used massive centrifuges, spinning them at mind-bending speeds to sift the energetic atoms away from the dead weight. The world saw the result of that race in 1945, with the little boy bomb dropped on Hiroshima. It was a staggering, terrifying display of what happens when uranium is enriched to the absolute extreme. But after the war, a new question emerged. Instead of destruction, what if this was used to build? Interestingly, nuclear power plants don't need uranium anywhere near weapons-grade levels. Most commercial reactors use fuel enriched to only about 3% to 5% U-235, enough to sustain a controlled chain reaction. Weapons-grade uranium is very different, usually enriched closer to 90%. That huge gap is why enrichment keeps showing up in international headlines. The concern isn't simply who has uranium, but how far they enrich it. That's why Iran draws so much attention. When uranium reaches around 60%, it's still below weapons grade, but much closer than ordinary reactor fuel. At that point, inspectors and governments pay close attention because the distance between civilian fuel and military potential has become much shorter. But put the politics aside for a second, because the same process that makes governments nervous is also what makes nuclear power so productive when it's tightly controlled. Today, those refined pellets help generate about 10% of the world's electricity. So where exactly does this green gold come from? Right now, three heavy hitters, Australia, Kazakhstan, and Canada, control over 60% of the world's uranium supply. Smaller deposits are scattered across many countries, and if a country has the technology to enrich it far enough, even ordinary uranium ore can become politically and militarily dangerous. Usually, uranium is found in tiny concentrations, maybe 1 or 2% of the rock, but if you head up to Saskatchewan, Canada, you'll find the holy grail of mining. Some of the ore there is over 20% pure. That is literally 100 times richer than the global average. But there's a catch. These high-grade deposits are often buried under thick layers of sandstone that are completely soaked with groundwater. Like you're trying to dig a hole in a giant wet sponge that's constantly trying to collapse on you. The moment a shovel hits the dirt, the water comes rushing in. To beat this, engineers came up with something straight out of a sci-fi movie. They freeze the ground. They drill hundreds of deep holes and pump a super chilled salt solution at a frigid 22 degrees Fahrenheit through a massive network of pipes. This creates a literal ice cage, a solid waterproof wall of frozen earth. Only then can they safely mine the uranium without the tunnels turning into a swimming pool. In February and March of this year, Canada officially greenlit its first 2 new uranium mines in over 20 years, Wheeler River and Rook I. The Wheeler River project is a total game changer because of a technology called in situ recovery, or ISR. Instead of digging massive open pits or building elaborate ice fortresses, they just drill small holes, about the size of a dinner plate. They send a mild solution down to dissolve the uranium right where it sits, then pump it back to the surface. Compared with traditional mining, it uses far less water, creates very little solid waste, and disturbs much less of the land above. Mining uranium isn't like chipping away at coal or panning for gold. Because this ore is highly radioactive, engineers can't just send crews down into the tunnels with pickaxes and shovels. Instead, they've turned these mines into a high-tech playground for remote-controlled robots. The real secret sauce is a unique technology used by the industry giant Cameco called jet boring. Here's how it works. Engineers drill a tunnel underneath the frozen ore and send in a robot. This machine blasts the rock with water at a staggering 15,000 psi. It cuts through solid rock with surprising ease, turning the uranium into a liquid slurry that gets pumped straight to the surface. The beauty of this system is that the workers never actually touch the radioactive dust, and there's zero risk of a tunnel collapse putting lives in danger. Plus, the air inside the mine is completely swapped out for fresh air every 20 minutes, keeping the environment clinical and safe. In the last year, things have gotten even more sci-fi. The industry has started leaning hard into artificial intelligence. By using machine learning to calculate the water pressure and spray angles down to the millimeter, production has skyrocketed. In 2025, the famous Cigar Lake mine absolutely shattered records, cranking out 19.1 million pounds of uranium, way more than anyone expected. Moving through 2026, they're keeping that momentum going, showing that some of the most dangerous jobs in this industry are increasingly being handled by machines. Once that uranium is pulled from the earth, it's ground down like sand and sent to a processing plant. There, engineers give the ore an acid bath, which sounds intense, but the goal is simple: dissolve the valuable uranium and separate it from the unwanted rock. After that, the uranium goes through several more steps. It's converted into a gas, enriched so it has enough uranium-235 for most modern reactors, and then turned back into a fine uranium dioxide powder. From there, the powder is pressed under huge pressure into small ceramic pellets. These pellets are then baked in an industrial furnace until they become dense, rock-solid pieces of nuclear fuel. Next, the pellets are stacked inside long tubes made from zirconium alloy. And zirconium matters because it can handle extreme heat and corrosion while still allowing neutrons to pass through and keep the reaction going. Those sealed tubes become fuel rods. Then, depending on the reactor design, more than 100 fuel rods can be bundled together into one fuel assembly, a carefully engineered package built to sit inside the reactor core. And for anyone worried about the glow-in-the-dark factor, fresh fuel is radioactive, but not in the dramatic movie monster way people imagine. At this stage, workers can handle it with standard industrial precautions. It's a clean, precise end to a very long journey from the bottom of a mine to the heart of a power plant. Once these fuel assemblies finally arrive at the power plant, the real show begins. Welcome to the heart of the operation, the reactor core, where that tiny pellet's hidden energy finally gets released. Inside, hundreds of fuel assemblies are arranged with extreme precision. When the process begins, tiny particles called neutrons start moving through the core. They hit uranium-235 atoms, causing them to split. Each split releases heat along with more neutrons, which can go on to split more atoms. That's the chain reaction, powerful but carefully controlled. And that word controlled matters. This isn't energy just running wild. The reactor is built with layers of safety systems, including control rods that can absorb neutrons and slow the reaction down, cooling systems that carry heat away, and thick containment structures designed to keep the process sealed off from the outside world. When you strip away the high-tech labels, a nuclear reactor is basically a massive, super-powered water heater. Fission creates heat. That heat turns water into steam. The steam spins a turbine. The turbine drives a generator, and the generator sends electricity out to the grid. The payoff is huge. A single large nuclear reactor can produce hundreds of megawatts, sometimes over 1,000 megawatts, of steady electricity. That's enough to power hundreds of thousands of homes day and night without needing sunlight, wind, or a trainload of fuel arriving every few hours. After spending several years inside the reactor, these fuel assemblies finally reach retirement. But obviously, they aren't getting tossed out on the curb for Tuesday morning trash pickup. Even after they're spent, they're still incredibly hot and radioactive. So first, they're moved into deep spent fuel pools, where water does two jobs at once. It cools the fuel and shields workers from radiation. These pools are usually about 40 feet deep, with plenty of water above the fuel, acting like a built-in radiation shield. After several years, often 5 to 10 years or more, the fuel can be moved into dry casks, those massive sealed containers built for long-term storage. That sounds scary, but the amount of material is surprisingly compact. In the US, all the spent nuclear fuel produced by commercial reactors over decades would fit on a single football field stacked less than 10 yards high. Compare that to coal power plants, which produce huge amounts of ash every year, waste that can contain heavy metals and even naturally occurring radioactive material. Nuclear waste is dangerous, no question. But it is also carefully tracked, sealed, and contained in a way most industrial waste simply isn't. And this is where the story gets more interesting. In early 2026, the US Department of Energy restarted uranium recovery operations at the H Canyon facility at the Savannah River site. The goal is to recover valuable uranium from existing nuclear materials and support production of HALEU, a specialized fuel expected to play a major role in advanced reactors. That doesn't mean every spent fuel rod is magically becoming tomorrow's clean battery. The process is complicated, expensive, and tightly controlled. But it does show why nuclear waste is not as simple as trash. Some of it may still contain valuable energy for the next generation of reactors, including small modular reactors designed to provide steady power for factories, cities, and yes, even the massive AI data centers everyone keeps talking about. Of course, the debate is still fierce. On one side, supporters argue, I'd rather live near sealed nuclear waste than breathe coal pollution every day. On the other side, skeptics ask a hard question. Even if the waste is compact and controlled, is it fair to leave radioactive material for future generations to manage? So which side are you on? Drop your best argument in the comments. I'm curious to see where you land on this one. Thanks for watching. If you enjoyed this deep dive, hit like, subscribe, and ring the bell so you don't miss the next mystery we decode. See you in the next one.